We next talked about the concepts of potential energy and potential in electric fields. So if we have an electric field and we put a charge Q in it, it will experience a force, and the force will equal Q times the electric field. So the electric field will accelerate the charge if it's a positive charge to the right, and it will gain kinetic energy. So if you take the charge instead and move it to the left, you will have to do some work to move the charge to the left. So that would be like increasing its potential energy. So for this pictured electric field, on the left-hand side would be a higher potential energy than the left-hand side, or than the right-hand side. Okay, so if we take this charge and we move it at a right angle to the electric field, the electric force from the electric field is not opposing it, so you're doing no work. If you take the charge and move it against the electric field, it takes some force to do that. The force you're applying is minus Q times the electric field. So moving it along this segment, you have to do work. And if you let the electric field accelerate the charge to the right, you're extracting energy. The potential energy in the field is being converted to kinetic energy of this charged particle. Now let's determine the amount of work done moving Q along this path dl that makes some angle theta with the electric field. Now moving along path dl is the same as moving along these two paths. The first path directly into the electric field, and then this second path perpendicular to the electric field. So when we're moving perpendicular to the electric field, no work is being done. All the work is done on this first segment, and the length of this first segment is the hypotenuse of this triangle, d sub L, times the cosine of this angle, which is the cosine of 180 degrees minus theta. So the work is going to equal the force, and the force you're applying, the magnitude of the force, is Q times the electric field through this distance being dl cosine of 180 minus theta. And cosine of 180 minus theta is minus cosine of theta. So we have the magnitude of the electric field times the magnitude of our displacement times the cosine of the angle in between them. That's just the definition of the dot product between the electric field intensity and our displacement. So the work involved in moving along this displacement dl is minus QE dot dl. So now if we think about taking a charge in an electric field, a charge Q, and moving it from, say, location A here to location B, and let's designate some path. Then we can break up this path into all these little d sub L segments, and we know the work involved in each individual segment. That is just minus Q times the dot product between the electric field and our displacement. So the amount of work it takes to go from A to B is minus the integral of Q times the electric field dot dl. Now we define the potential difference between point A and point B as the amount of work it takes to move 1 coulomb of charge from A to B. Or you can think of that as the amount of work per unit charge. And the units we give for potential difference is volts, and we see, looking here then, a volt is an amount of work per charge, or a joule per coulomb. So 1 volt is equal to 1 joule per coulomb. Let's look at the potential associated with a point charge. So let's put that point charge at the origin. And we know the electric field intensity associated with that point charge is Q over 4 pi epsilon sub 0 r squared in the a sub r direction. So if we're looking at the potential difference between 2 points A and B, it's minus the integral from A to B of E dot dl. Okay, so for this field, for a point charge then, we put in our electric field, and we dot it with our differential length. And when we're dealing with spherical coordinates, which we will be because of this spherical symmetry, the length differential is dr in the r direction plus r d theta in the theta direction plus r sine of theta d phi in the phi direction. And so when we look at this, the AR dot A theta is 0 and AR dot A phi is 0. So we're left with the integral from A to B of Q over 4 pi epsilon sub 0 r squared dr. Okay, so now the only variable we're left with is r. So at position A, r has some value r sub A, and at position B it has some value r sub B. Okay, so if we perform this integral then, the potential difference between points A and B, this integral will be Q over 4 pi epsilon sub 0 times r evaluated between r sub A and r sub B, or Q over 4 pi epsilon sub 0 1 over r sub B minus 1 over r sub A. And when we think about it, the result of this dot product we know is because the only time you're doing work is when you're moving in the radial direction. So it doesn't matter how you get, say, from point B to A, because the only time you're doing work is when you're moving in the radial direction. So you could move like this. You're doing work along this first segment, no work on the second segment, or you could have moved like this, where you're doing no work on this segment and only work on this radial component. Now let's think about the amount of work it takes to move a 1 coulomb charge from infinity to some location r. Okay, so what that means is we'll start at infinity, so A will be at infinity, so r sub A here will be infinity, and r sub B will be our final location. So looking here, r sub A will be infinity, so this term will go to 0. So what we have then is V sub B is our potential at location r. V at A, our starting point, is at infinity, so the voltage at infinity, and that's going to equal Q over 4 pi epsilon sub 0 times r. Now, the only thing that is measurable is potential difference. In other words, how much work does it take to move a charge from infinity to some location r? And so we can actually pick a reference however we want to. Often when you're talking about just point charges like this, as your book does, it will choose the potential at infinity being 0. But I want to emphasize that what this expression here gives us is really the amount of work to move 1 coulomb of charge from infinity to V sub r. So your potential for a point charge is usually just written like this in your textbook. So for point charge Q at the origin, at some location R here, the potential difference between location R and infinity is Q over 4 pi epsilon sub 0 R. Okay, so now let's change location of the origin. So let's say this is where Q is. This is where we want to find our potential. It's still the same distance away as in this illustration above, but now the origin is here. So R, again, which is a different R now, is going to point to where we want to find the potential difference between R and infinity. And let's call this positioning of Q R prime. It should take the same amount of work to bring 1 coulomb of charge to this distance away from Q as here. It should be independent of the origin. And so we can just look at this equation and know that the result is going to be Q over 4 pi epsilon sub 0 times this distance right here. And let's call this distance D. And D here is going to equal R minus R prime. Or in other words, the potential difference is given as Q over 4 pi epsilon sub 0, the magnitude of R minus R prime. So now we're in the position to determine the potential if we have more than 1 point charge. So let's assume we have 2 point charges, Q1 and Q2. Here's the origin. So Q1 is at location R1, Q2 at location R2, and then we want to find the potential at some point located at R. Now again, the way you would find this potential difference between location R and infinity is the integral from infinity to location of R of E dot dl. But this electric field can be determined using superposition. It's equal to the electric field just due to charge Q1 plus the electric field just due to charge Q2. So this integral is minus the integral from infinity to R of E1 dot dl minus the integral from infinity to R of E2 dot dl. So because superposition holds in determining the electric field from multiple point charges, it will also hold for determining the potentials. So the potential difference between location R and infinity is the sum of the potential difference because of charge Q1 plus the potential difference due to charge Q2. So we can write this then as the voltage at location R is equal to Q1 over 4 pi epsilon sub 0 times the distance from Q1 to our point we're trying to find the potential, which is just the magnitude of R minus R1, plus Q2 over 4 pi epsilon sub 0 times the magnitude of the distance from Q2 to the location where we're trying to find the potential. And so it's straightforward now if we have n charges, the resulting potential at some location r is 1 over 4 pi epsilon sub 0 times the sum from k is equal to 1 to n of q sub k over 4 pi epsilon sub 0 times the magnitude of r minus r sub k. This result for collection of point charges will enable us to determine the potential if we have some charge distribution. So let's assume we have this structure that has rho sub v coulombs per cubic meter. Here's the origin. Here's the point where we want to know the potential. And we can break up this structure into these differential volumes. And the amount of charge associated with each of these differential volumes we'll call dq, and it will equal rho sub v dv. And let me call this dv prime because I'm going to put the location of that differential volume at r sub prime. So the potential now at location r will depend inversely on this separation between our charge packet and the point we want to find the potential, as in this expression. So for just this charge packet dq, the potential at r is equal to 1 over 4 pi epsilon sub 0 dq, which is rho sub v dv prime, over the magnitude of r minus r prime. So to get the potential at location r due to this whole charge distribution, it's just the integral of all these contributions to each little dq, or v is equal to the integral over the volume of 1 over 4 pi epsilon sub 0 rho sub v dv prime over the magnitude of r minus r prime. So given an electric field, we can find the potential field, the scalar potential field. Now we want to look at, if we have the scalar potential field, how would we determine the electric field intensity? So let's assume we have this little voltage probe that is of length delta L, and we put the probe somewhere and we can measure the voltage drop across it. So by that I mean the voltage at the tip minus the voltage at the tail, which we'll call delta V, is what is measured. Okay, so looking back at our expression here for the potential difference between points A and B, where now A is the tail and B would be the tip, delta V is minus the integral from tail to tip of E dot dl. Now we're going to assume delta L is short, so we can approximate the electric field as being constant along delta L. So I can write this as minus E dot the integral from tail to tip of dl. So the integral from tail to tip of dl is just delta L. So this is equal to minus E dot delta L. Okay, so now I want to look at the different coordinate systems and how we can then determine the electric field intensity given the scalar potential field. Okay, so we're at some location in a Cartesian coordinate system, and we know the voltage, the potential field everywhere. Okay, so now we're going to come in with this differential probe of length delta L, and let's assume we can also vary the length of delta L before we insert it into our field. And so let's align it with the x-axis and make its length equal to dx. So in other words, when I put my probe in like this, I can think of delta L as d sub x in the x direction. And I'll measure some voltage across it, which will essentially be dV. Okay, so let me put these two results in this equation up here. So dV is then equal to minus E dot delta L, which is going to be dx in the x direction. So E dot A sub x is just going to be the electric field in the x direction. And then solving for E sub x, I see it's equal to minus dV dx. And you can make this argument then for finding the electric field in the y direction and the component of the electric field in the z direction. Okay, so then in Cartesian coordinates, to find the electric field, given the potential field, it's equal to minus dV dx in the x direction, minus dV dy in the y direction, minus dV dz in the z direction. So shorthand way we designate that is as minus the gradient of v, where remember this del operator is partial with respect to x in the x direction plus partial with respect to y in the y direction plus partial with respect to z in the z direction. Okay, so now let's go back to this point and think in terms of a polar representation. Okay, so now what we want to do is bring in this little voltage probe, and let's put it, say, in the rho direction. And we're going to make its length equal to d rho. So in this case now, delta L is equal to d rho a sub rho, and the voltage drop we measure across our voltage probe is just dV. So now let's go back to this expression and plug in for delta V and delta L. So we have dV is equal to minus E dot d rho a sub rho. So E dot a sub rho is just the electric field in the rho direction. So solving for E sub rho, it's equal to minus dV d rho. And you can make the argument that the z component is identical as in Cartesian coordinates. So E sub z is equal to minus dV dz. And now we have one more to find, the electric field in the phi direction. And this is the one that's going to be a little bit different. So now if we change phi by an amount d phi, we will move this distance here, which will depend on the coordinate rho. So this length will be rho d phi. So now what we want to do is adjust our voltage probe so it's of length rho d phi. So now delta L is going to equal rho d phi in length, and it's going to point in the a sub phi direction. And again, the voltage measured now across our voltage probe, since we're moving length rho d phi, will be dV. So let's make these substitutions in here for delta V and delta L. So we'll have dV is equal to minus E dot rho d phi in the a sub phi direction. So E dot a sub phi will give us the component of the electric field in the phi direction. So now we can solve for E sub phi. E sub phi is going to equal minus 1 over rho dV d phi. Okay, so if we collect these terms then, we see that we can write the electric field intensity in cylindrical coordinates as minus dV d rho in the a sub rho direction minus 1 over rho dV d phi in the a sub phi direction minus dV dz in the a sub z direction. So let's look at spherical coordinates. So when we change r by a differential amount dr, we move a distance dr. When theta changes by an amount d theta, the distance we move is r d theta, and when phi changes by an amount d phi, the distance we move is r sine of theta d phi. So we take our little adjustable voltage probe, we make it of length dr, and align it in the a sub r direction here. So delta L is equal to dr in the r direction, and the voltage we'll measure across it is dV. So in our expression here, delta V becomes dV, and delta L is dr a sub r. So E dot AR will give us the component of the electric field in the r direction. So solving for E sub r, we get E sub r is equal to minus dV dr. Okay, so now we'll take our little adjustable voltage probe, put it in the a theta direction, and adjust it to length r d theta. So then delta L will be r d theta in the theta direction, and the voltage we'll measure, delta V, is dV. So substituting now in our expression here, we have dV is equal to minus E dot r d theta a sub theta. So E dot a sub theta will give us the electric field in the theta direction. So solving for E theta, we get E sub theta is equal to minus 1 over r dV d theta. Okay, and finally we're going to take our little probe, put it in the a phi direction, and adjust it so its length is r sine of theta d phi, the differential length in the phi direction. So delta L is going to equal r sine of theta d phi a sub phi, and the voltage we measure across our little probe is dV. So now substituting in our expression here, we have dV is equal to minus E dot delta L, which is r sine of theta d phi a sub phi. So E dot a sub phi will give us the electric field in the phi direction. So solving for E sub phi, we see it's equal to minus 1 over r sine of theta dv d phi. So now let's collect those three components for the electric field in spherical coordinates. So it's minus dv dr in the a sub r direction, minus 1 over r dv d theta in the theta direction, minus 1 over r sine of theta dv d phi in the a sub phi direction.